Hello and welcome to Game Revolutions, the series where I write a Moon Patrol clone game before your very eyes, and marvel at how easy coding is for me. I just never seem to write bugs. Last time we introduced the fearsome feeblah enemy. Today we go over the code that shows how it all works. But first, we get the feeblah to move, and then we add more feeblahs onto the screen at once, and we get them to all swarm around and menace our lunar rover. Will anybody survive? And then you'll add the intro right after that, kind of build the dramatic tension, and then hopefully people will want to keep watching, go through the intro and not stop there like they have done in the past. Anyway, glad to have you aboard to do the editing. I think things are going to go a lot smoother. Okay, I've added some code to move the feeblah in a particular pattern. I added a structure where the first field is the displacement, so that is relative to where the feeblah was just before. How much should it move? Where should it move? And then this is a repeat of how many times to do that displacement. How many frames should I continue to do that displacement? Here's the data. Maybe looking through the data will help it make a bit more sense. So the first element here says move to the left by 1 pixel 10 times. So over the course of 10 different frames, it'll keep moving to the left by 1 pixel. Then move down a line and left 1 pixel, 12 frames. Then move up a line and left a pixel for 12 frames. And then when I see that at the end, that means, okay, the feeblah is done and it should disappear. And once I have all this code working, I'll walk through how it works. But this is just the general idea. So let's see. And the nice thing is I can change this pattern. I can do a bit of trial and error. And if I like how it looks, great. If I don't, I can start making some tweaks. I don't have to change any code. I just change this. Okay. I mean, keep in mind, this is really the first time I'm testing the erasing code. So obviously that was never working. The motion is not quite what I was expecting. It just seems to just keep on going and going, left and down, left and down. Yikes. Should we let it rip, folks? There we go. And it has crashed everything. Screen memory is just memory, and at some point it's going to race up to your code or your stack or whatever, and then you get this. Okay, I found a few obvious bugs. Some misuse of registers. I was using the wrong registers again. And then there was another spot where I was using the wrong conditional branch. I was doing equal instead of high. This probably isn't going to fix everything, but let's... definitely not fixing everything. Oh, but it's moving. It went down and now it's going up. So it is kind of going through the motion. The buffers seem a bit wrong. It seems to be drawing bytes that it's not supposed to be drawing. So probably the place that figures out the source bytes to copy from is getting some code instead of the data. Doesn't look like it'll crash though, because it's not going outside of screen memory. Let's speed it up. Go into turbo mode. Yeah, I bet it'll run like this forever. So that's a step in the right direction. Okay, I just stepped through everything like I should have done from the first point, and I went through it in the debugger and just very carefully looked at all the things I was trying to do, making sure I did it right. I found several things that needed fixing. Several things. So let's see. Oh, yes. Yes, yes, yes. I mean, it's not supposed to wrap around like that. My path clearly needs to be adjusted, but it is, yeah, when I hit the 0, 0, so it disappeared just like it's supposed to. Let's check that out again. But it's symmetric, it's animating, it's the buffer it's using is the right buffer. Like, and it's going forward, backward, forward, backward. Maybe it should be faster. I mean, that doesn't look like Galaxians. When I start adding more of them, I don't want them to march like the slow Space Invaders. I want them to kind of swarm around. So I need some work on the speed. I need some work on the path. And then I can maybe start introducing more. Okay, I've made some tweaks to the speed and the path. Let's see what I have now. Oh, yeah. Oh, yeah. Oh, yeah. Oh, yeah. Zipping in and going away. Zipping in and going away. Okay. Sure, there's some issues here, I see. Okay, now not the, but here, there, these things here, yeah. Okay. I do have to deal with that, but I think maybe I don't have to deal with that. You know what I think is happening is the bullet bites erase themselves by redrawing what they were before the bullet was drawn. And if the enemy was in the way, then pieces of the enemy are getting drawn in the place of the bullet as it erases itself. And I think that'll be a non-issue once the bullets don't actually go through the enemy, once the enemy actually blows up. I think it'll solve itself. I'm not going to worry about that. I think the next step is to make them swarm, more than one feeblah at a time, which, if I've done the code correctly, should be simple because I already have arrays of structs anyway. It's just a matter of invoking the new feeblah routine multiple times to make a whole bunch of them. Okay, baby steps. I have fixed it so there are 2 feeblahs instead of just 1. Oh yeah, look at that, look at that. Zoom in, zoom out. Okay, cool. I'm pleased. Okay, I have successfully tested 6 feeblahs swarming in and swarming out. It looks pretty good. I'm pretty happy with it. I'm going to show it to you. But first, it's time to finally go over all this code that I've only been showing you glimpses of so you see an idea of how it's done. Starting with the data, I have an array of feeblah info structs. Each instance of this struct represents a single feeblah that's on the screen at once, and it represents its state. First up, we have a 1-byte set of flags. If you imagine these are the bits in the flags, this bit tells me whether that struct is used or not. The high bit is 1 if we're animating backward, and it is 0 if we're animating forward. There are 3 different frames to the feeblah, frame 0, frame 1, and frame 2. And the idea is we show frame 0, then frame 1, then frame 2. This is where the feet are together. And then we go in reverse. Then we go back to feeblah frame 1, and then back to feeblah frame 0 where the legs are apart. And so it just bounces back and forth, back and forth. So this is 0 when we're going forward, and it's 1 when we're going backward. Finally, the rest of these bits are a timer. And I'm not even using all of them because that would make it too slow. But the idea is it counts down until the next time it's time to animate and move the feeblah. So I use this as a kind of pause to slow down its movement. Next up is a 2-byte offset. This tells you where the feeblah is supposed to live in the screen, and it's relative to this, feeblah offset base, which is 30 bytes after the end of the rotating background. So after the end of the mountains or the alien buildings, which we haven't seen in a while, that's where the offset base is. And rotate BG after itself is relative to the particular screen buffer we care about. So even rotate BG after is not an absolute value. It is relative to a particular screen buffer. The next 2 bytes are about the movement of the feeblah, and I'll talk about them later. And then finally, this is a pointer to where the bytes that we're drawing for the next frame live. So for example, it might point here, or it might point here, and so on. The array of these structures is global. It is not local to a particular screen buffer. And here is where that global array is stored. Right now, maximum feeblahs is just 6, so we have enough space for 6 of them. But the feeblah draw info struct is specific to a buffer. So we're going to have an array of these for buffer A and an array of these for buffer B. We have one byte that tells us whether this particular feeblah draw info struct is used. And then we have another to tell us where in the buffer we actually last drew this feeblah. This way, no matter where the feeblah is going, what direction it's going in, we always know where we last drew it in a buffer, so we know how to erase it from that buffer. This is where we store the array of feeblah draw infos, and you'll see that that is simply a field within the buffer info struct, and we've got 2 of these for the 2 buffers. And the final structure is the feeblah movement structure, which I already went over. The displacement followed by a repeat of how many times to do that displacement. The displacement followed by a repeat to tell us how many times to do that displacement. Over and over again, pair, until we hit a 0, 0 that tells us we're done. And so this displacement and this count correlate to the movement index and movement timer in the feeblah info struct. Movement index tells us the offset into the table of feeblah movement structs so that we know which one we're on right now. And movement timer is the countdown that starts at count and goes down to 0. So that's how we keep track of how many more times to repeat this displacement. So how do we get the feeblahs onto the screen? You may recall that I have this level progress table. It tells us what kind of challenge or obstacle should occur and at what time. After 10 ticks, add a new feeblah. After 3 more ticks, add a new feeblah. After 3 more ticks, add a new feeblah. And also, let's add some rocks, let's add some holes, let's add another swarm of feeblahs. Let's add a rock, let's add a hole, let's add another swarm of feeblahs. So the new thing here is the action new feeblah. It's defined up here, but the really important part is the jump table includes new feeblah at its proper location, so that as we read the progress table, this tells us, oh, if the value is 6, then we're going to jump to this word, because that is at an offset of 6, and then we're going to call that routine. New feeblah goes into the array of feeblah info structs, and we loop through until we find one that's unused. You'll notice my pointer is using X. B includes the size of the struct, so I can continue to use ABX each time through the loop and very quickly advance to the next struct. If we find an unused struct, then we just initialize all the fields. We start off saying that it's used and we just set the timer to 1 tick. That way the code you see later will automatically initialize everything once that goes down to 0. The initial offset is set to 30, so that translates to the right-hand side of the screen. And then we initialize 2 fields at once using this neat trick that someone taught me. Since D is really just an amalgam of A and B, this neat line here loads A with FF and B with 0, 1. And then this stores FF and 0, 1 next to each other. That means the movement index field will start off being -1, which is the FF, and the movement timer starts off being 1. That way, as soon as it decrements down to 0, the other code will take over and initialize those. Finally, I initialize the byte start address to be the beginning of the first frame, -24, so that the first time through the code you're about to see, it will advance it to feeblah 0 data. Here's the main loop of the whole game, and each time through we call draw feeblahs, which is where all the code we care about lives. The first thing it does is it has a loop which goes through each used feeblah draw info structure, grabs the offset, and then erases a feeblah-sized chunk starting at that offset. Erase feeblah is simply a fast way to take this word, which is just 2 green bytes, and store it in as many rows as we need to erase the feeblah. And this is using a couple nifty tricks that I've shown in previous videos. I take full advantage of the small offset. Recall that when using indexed addressing, if I can keep my offset down to just 8 bits, I only have to pay 1 extra cycle for that offset. As soon as I need to do more than 8 bits, I'm up to 4 extra cycles, so I definitely don't want to do that. And note that the 8 bits are treated as signs, so I want to keep my offsets between -128 and 127. So that's why I can go up to 3 rows below and 4 rows above. After that, I have to readjust my pointer so I can continue to use the 8-bit offsets. And it is actually worth doing this extra instruction to adjust the pointer so I don't have to use 16-bit offsets afterward. Once the erasing is done, I then go through my global array of feeblah infos. I have X pointing to the next feeblah info that's used. I have U pointing to the next feeblah draw info, because I need to write into the draw info where the offset ended up being for the feeblah I just drew. Since I need to use U for other purposes, I'm using a bit of self-modifying code to store the U for later. This is going to be faster than trying to push it onto the stack. df get next feeblah draw info is merely a label before it's time to restore U with whatever byte I wrote over here. So when I do that store, I'm actually changing the instruction, in particular the operand of the instruction, so that later when I load U, I'll be loading that value that I had just stored. And here's the loop that adjusts the state of the feeblah. Once I've found a feeblah info in use, I decrement the counter. Remember, it's using these bits, so I want to subtract 1 from this bit, and then whatever carries are necessary will advance to the other bits, which means I want to subtract binary 1, 0. I then extract the timer bits, and if it's not 0 yet, I just don't modify the state at all. I just move on to the draw, which will end up redrawing it in its old spot. But once the timer does go to 0, I need to animate it and I need to move it. I grab the flags, I reset the timer back to 2, and here's where I have to confess I'm actually, as it turns out, not using that timer at all. I'm not slowing anything down at all. Since these are the timer bits, I'm effectively just setting the timer to 1, so that the next time around, I can decrease it down to 0 and do stuff. I will be animating and moving at every frame. It turns out that I just preferred the movement this way after all. But what I might end up doing is at different stages of the game, I might choose to have different timers. So I might have them going a bit slower in some places and then gradually get faster and faster. So I'm leaving the timer in there, but you should know I'm actually, as it turns out, not using it. Next, I point U to the frame I'm going to render, the source bytes. I store the updated flags, and since I stored them, that will set the condition code, and I can ask if I'm animating backward. Remember, that top bit tells us if I'm going backward. So if I got a less than, then I'm going backward, otherwise I'm going forward. And the only difference is how I advance U. When I go forward, I add fibble byte count. And when I go backward, I subtract fibble byte count. In both cases, I need to check if it's time to toggle the direction, meaning I was going forward through the frames, and now, right now, I need to go backward. So I've got to bounce back and forth when I hit the boundaries. That simply involves toggling that upper bit, saving the flags, and then basically starting over again. Next up, we decide whether and how to move. So I use that trick again where I load both A and B with 2 fields at once. A gives us the index into that displacement table, and B tells us how many times we have left to repeat that last displacement. I decrement B, and if we're down to 0, then that means it's time to advance to the next displacement. Advancing to the next displacement means we need to increase our offset. Remember that in the feeblah info structure. Multiply by 2 so it's a decent offset into the move table. Point to the move table, offset into the move table, check if it's that 0, 0 at the end, in which case we have to delete the feeblah. Otherwise, store the count we read from the displacement table into the movement timer, thus initializing the timer, and then go back. So at this point, one way or another, the register A has the displacement offset. So we grab the initial offset of the feeblah, wherever it was supposed to be. We add A to that, and that is now what we store as the current offset for the feeblah. And finally, we draw! And a bit more self-modifying code. Since X points at the feeblah info structure that we're using, and we're going to trash it, and we want to restore it, we're just going to store it inside the load instruction. So this stores it here, so that when we're all done, we can retrieve it. So let's take a look at the draw. The two registers that I keep around through the whole thing are Y, which points into the screen buffer. That's where I'm writing stuff to. And I'm going to use the stack register S to point to those frame bytes so I can retrieve them all very quickly, 6 bytes at a time. So using stack blasting, I retrieve 6 bytes, and then I store D, X, and U into the screen. Retrieve another 6 bytes, store them into the screen. Retrieve another 6 bytes, store them into the screen. And once again, I'm using that trick where I ensure that my offset is always 8 bits. Y is the register I'm offsetting from. And as soon as I need to update Y, I do so here so I can keep my offset at 8 bits. You'll notice that although I'm using Y, I never do a load Y or a store Y. Regardless of the addressing mode, Y always takes 1 cycle longer than X or D. But LEA uses the same number of cycles for all of them. Once I'm done drawing, I restore my X to point to the feeblah info structure. I restore my U to point to the feeblah draw info structure. And I take the offset that I just drew the feeblah at and I remember it in the feeblah draw info structure. That way, next time I'm on this screen buffer, I'll know where to erase it. And now we're at the end of the loop, so I simply advance my structure pointers and go back up. Once I've exhausted the array, I am finally done. Let's check it out. And yes, those artifacts are still there, but I'm pretty sure they'll go away once I figure out how to get them to explode. So as a final test, I'm going to run this under MAME. And I'm going to use my performance meter over here. As you might recall, before I added the feeblah, I was going about 30% frame remaining, the higher the better. So let's see what impact the feeblahs have. Keep your eye on the top meter since the average is probably going to be kind of mixing things up because there's spaces with feeblahs, spaces without. But generally it looks like we're going about between 10 and 20% when the feeblahs come on. So now there are no feeblahs. We're probably averaging about 30%. But watch what happens when they come back. Ooh, it goes down. Oh, that went even below 10%. 8%? Yeah. They make a marked difference in performance. And that's with all my nifty tricks, too. And of course, next, I have to add hit detection with the bullets and exploding when they go away. Not to mention they need to be dropping bullets on the car, too. A lot left to do and not necessarily that much frame time remaining to do it in. I'll figure something out. Next time we'll design some feeblah explosions and allow the lunar rover to actually shoot them and blow them up. Hopefully that will get rid of the artifacts that we were seeing before. Until next time, thank you for watching.